So, example 5. Now, consider the following reaction. Consider the following reaction. It is going to be ATP plus H2O, the hydrolysis of adenosine triphosphate, going to ADP plus inorganic phosphate. We have the delta G standard for this is equal to minus 30.5 kilojoules per mole of ATP. Now, delta G is under biochem standards, right? Is under biochem standards. Standards of pH equal to 7.0, or a hydrogen ion concentration equal to 10 to the minus 7. You know, I've never liked the notion of pH. It just really, really bothers me. It's always bothered me. We're dealing with concentrations. Let's just deal with concentrations. But pH is everywhere, so that's fine. So pH 7, that just means that the hydrogen ion concentration is 10 to the negative 7. Okay, now, here is our question. If we drop the pH to 4.0 from 7.0, in other words, if we make this environment more acidic, pH to 4.0, our question is, will the reaction above become more exergonic, or less exergonic? In other words, if we drop the pH and make it more acidic, is there going to be more free energy available to do work, or is there going to be less free energy able to do work? Is this going to get negative, more free energy, or is it going to get positive, less free energy? That's our question. And of course, the quantitative version, what will be, so there's the qualitative and the quantitative. What will be the new delta G standard under conditions of pH 4 instead of pH 7? That's the real question. Okay, well, qualitatively we can answer the first part as follows. So let me go ahead and draw a little bit of a line here. So qualitatively, we can answer the first part as follows. Here's where we get into the details of what it is that's going on. Often in biochemistry or in chemistry, you know, there are going to be different things in a given reaction. There are going to be different aspects that we're interested in. We don't want all of the details all the time. It's just going to clutter things up. In this particular case, we want the details. And what I mean by details is we want to talk about what's going on where. Where is each particle going, and what is the charge on each particle? Well, the hydrolysis of ATP actually takes place like this. So ATP is carrying a 4- charge. When it is hydrolyzed by a water molecule, it is going to form an ADP molecule, which is carrying a 3- charge, plus an inorganic phosphate, which in general is carrying a 2- charge, and it's going to have it's going to release some hydrogen ion into the aqueous medium. This is what is really going on. We didn't write that up here. Notice we didn't have this up there. Now, dropping the pH means raising the hydrogen ion concentration. Well, if you raise the hydrogen ion concentration, you know by Le Chatelier's principle that you're going to end up pushing the reaction that way. That's what's going to happen here. So qualitatively, you can answer this question. It's actually going to become less exergonic. There's going to be less free energy available. This negative 30.5 is going to get less negative. It's going to go up to maybe negative 20, negative 15, negative 10. Who knows? That's what happens. So it's good to know exactly what is going on in a particular reaction. In general, we don't really concern ourselves with stuff like that, but it really is a great idea to understand the details. So yes, we want you to have a big picture, But there are certain things, certain reactions that are so ubiquitous, we need you to know exactly what's happening. So this is what's going on. So dropping the pH will push the reaction that way. Okay, now let's do the quantitative. Now let's do the math. Okay, let's see what we can do here. I think I'm going to start that on the next page. So now so let's write this all out. The biochem standard, for delta G, it already accounts for a hydrogen ion concentration equal to 10 to, let me just write it here. It already accounts for the fact that the hydrogen ion concentration is equal to 10 to the minus 7 molar. Now, what we have to do is, well, let me write it out. Well, I'll say it. What we have to do is recover not the biochem standard, but the normal chemical standard that doesn't account for this, where we say 1 molar concentration of every species. Well, that 1 molar concentration also includes the hydrogen ion. So a 1 molar concentration, hydrogen ion, negative log of 1, you're going to get a pH of 0. But we can't do pH of 0. This is why the biochemical standard uses a pH of 7. That's why we have this thing right here, this standard plus that little mark that lets us know that we're at pH 7. However, in order to actually find what the new delta G standard is at a different pH, pH 4 in this case, we have to recover the original chemical standard and then work from there forward and find the new biochemical standard. That's what we're going to do. We're going to run 2 calculations. So what we have to do, and this is the kind of analysis that you want to think about. You want to understand what it is that we mean when we say biochemical standard. When you see some number like a reduction potential that says that we've accounted for a pH of 7, what does that mean? It means that we've taken the chemical standard, we've switched the number around, we've recalculated, and we've entered new numbers in this table. Well, in order to find a new standard, we have to go back to the original that we came from and then work forward from there. So what we have to do is recover that delta G standard, then calculate a new delta G standard biochem at a pH equal to 4. That's what we're doing. This pH 7, this pH 4. It's a new biochemical standard. So let's go ahead and actually recover our delta G. Well, here's the equation. The delta G biochemical standard is equal to the delta G chemical standard plus RT ln. Everything is the same. ADP PI, but this time the H is put in there. Now we're using the entire equation. See, this is where it comes from. We take the chemical standard, we recalculate using this equation for finding the new delta G by including the H. When we get this number, that's the number we put into the tables into biochemistry texts. So it is the delta G chemical standard plus RT ln with the actual hydrogen ion in the reaction quotient. There. Over ATP. Okay, now let's find, so this is our variable. We want to find this so that we can go backward from that. Well, we know what the delta G standard is. It's the negative 30.5. So our equation is negative 30,500, remember we're working in joules, equals the chemical standard plus 8.315 times 298 times the logarithm of, well, the concentration of ADP is 1, the concentration of PI is 1, the hydrogen ion concentration at pH 7 is 10 to the minus 7, the concentration of ATP is 1. When we do this and solve for delta G, what we get is the following. Delta G chemical standard equals 9,438 joules per mole. Notice, this is positive. So this is our chemical standard. We've recovered it from the biochem standard. We've just worked this equation backwards. Instead of looking for something on the left side of the equation, we're looking for this thing. So now we take this number and we readjust using a pH of 4, or a hydrogen ion concentration of 10 to the negative 4. So we go delta G biochem standard for a pH equal to 4 is going to equal 9,438 plus same thing, 8.315, the RT, 8 plus 8.315, 8.315 times our 298 times the logarithm of, again, this time it's 1 for ADP, it is 1 for PI, except now it is going to be 10 to the minus 4 over 1 for ATP. Okay? When we run this calculation, we end up with the following number. Delta G standard for a pH equals 4 is equal to minus 13,384 joules per mole, or minus 13.4 kilojoules per mole. Notice, this has confirmed the fact that it is less exergonic than the negative 30.5. We knew what it was going to happen qualitatively. Now we took care of it quantitatively. This confirms it. And that's it. So again, the biochem standard accounts for the pH equaling 7, the hydrogen ion concentration being 10 to the negative 7. I have to use that equation to actually recover the chemical standard, and from there calculate a new biochemical standard by including the pH now, which is 4, or the hydrogen ion concentration being 10 to the negative 4. I hope that makes sense. Thank you for joining us here at Educator.com. We will see you next time for more problems on bioenergy.